Google's quantum leap. The universe is governed by laws that are both elegant and profoundly strange. But what if our universe is just one of countless others, a single bubble in a cosmic foam of parallel realities? On July 22, 2025, Google's Willow quantum chip has forced us to confront the deepest mysteries of existence. The Willow chip, cooled to temperatures colder than deep space, performed a task so complex it would take our mightiest supercomputers eons to complete. This achievement, known as quantum supremacy, reignites the mind-bending many-worlds interpretation, the multiverse. Hartmut Nevin of Google's Quantum AI Lab suggests Willow may be tapping into resources of other universes, performing calculations across a vast network of parallel worlds. The journey to understand this revelation is just beginning. To truly grasp the magnitude of Google's achievement, we must first journey into the strange and counterintuitive world of quantum mechanics, a realm where the rules of reality as we know them are turned upside down. Classical computers, the kind we use every day, rely on bits, tiny switches that can be either 0 or 1, on or off. Every photo, message, or calculation is ultimately built from these simple building blocks. But the universe at its core is not so straightforward. It's a realm of probability and uncertainty, where particles can exist in multiple states at once, and outcomes are never fully determined until we look. Quantum computers use qubits, which, thanks to the phenomenon of superposition, can be 0, 1, or both at the same time. This means a single qubit can hold far more information than a classical bit ever could. With each additional qubit, the number of possible states grows exponentially. In fact, a quantum computer with just a few hundred qubits could represent more states than there are atoms in the observable universe, a staggering leap in computational power. Qubits also exhibit a mysterious property called entanglement, what Einstein famously called spooky action at a distance. When qubits are entangled, the state of one instantly influences the state of another, no matter how far apart they are. This interconnectedness allows quantum computers to perform many calculations in parallel, exploring countless possibilities at once, something that's simply impossible for even the fastest classical supercomputers. Quantum computers aren't just faster, they're fundamentally different. They harness the bizarre laws of quantum reality, opening doors to new kinds of problem-solving and discovery. They operate in a ghostly realm of superposition and entanglement, where particles can be in many places at once, and information can be shared instantly across vast distances. This is what gives quantum computing its revolutionary potential, solving problems that would take classical computers millions of years in just seconds or minutes. The Willow chip is our most fluent speaker of the universe's native language, designed to manipulate and read out quantum information with unprecedented precision. It's a machine that doesn't just compute, it thinks in quantum, opening a new chapter in the story of technology and human understanding. The world's attention was captured by a single, extraordinary experiment, one that would mark a turning point in the history of computing. Headlines blazed across the globe and scientists gathered to witness a feat once thought impossible. At the heart of this breakthrough was Google's Willow chip, a marvel of engineering with 105 qubits. It was tasked with random circuit sampling, a challenge akin to navigating a maze with more possible paths than there are atoms in the universe. Each qubit, delicately controlled, contributed to a computation so complex that it defied traditional logic. For classical computers, this problem is a nightmare. They must painstakingly calculate every possible path, one by one, consuming unimaginable amounts of time and energy. Even the most advanced supercomputers are left overwhelmed, their processors pushed to the brink. Yet Willow completed the computation in under 5 minutes, a result that stunned the scientific community and sent ripples through the world of technology. To put this achievement in perspective, the same task would take the world's fastest supercomputer an estimated 10 septillion years. That's a number so vast it's almost beyond comprehension. Imagine a time span longer than the age of the universe, multiplied by itself 1 trillion times. That's how far classical machines lag behind in this quantum race. This is quantum supremacy, a moment when a quantum computer achieves what no classical computer possibly can. It's a milestone that redefines the boundaries of computation. The random circuit sampling task is a benchmark, not a practical application, at least not yet. But it proves a crucial point. Quantum computers are now operating in a realm inaccessible to classical machines. Willow's success is also a triumph of error correction, stabilizing fragile quantum states that would otherwise collapse. This delicate balance is essential for reliable quantum computation. For the first time, arrays of qubits are demonstrating longer lifetimes than individual ones, thanks to sophisticated error correction techniques and engineering breakthroughs. This proves that error correction systems are not just theoretical, they're working, and they're paving the way for more powerful quantum machines. It's a crucial step toward building the quantum computers of the future, machines that could one day solve problems far beyond our current imagination. Where does this colossal computing power come from? Enter the many worlds interpretation. Hugh Everett proposed that every quantum measurement splits the universe, creating parallel realities. Each possible outcome becomes real in its own universe, branching into an infinite multiverse. David Deutsch later argued that quantum computers are evidence for the multiverse. A quantum computer in this view is a trans-universal machine, calculating across countless parallel worlds. Willow's speed is no longer a mystery, it's outsourcing computation to parallel versions of itself. The final answer is the result of interference between all these parallel computations. The solution in our world is assembled from echoes of calculations in others. Google's achievement may be the first tangible hint that these other worlds are more than fantasy. The implications are staggering. The idea that Willow is powered by parallel universes has ignited fierce debate. Visionaries like Hartmut Neven see quantum computers as windows onto the multiverse, validating the many worlds interpretation. For them, every quantum computation is an experiment in the structure of reality. This view transforms quantum computers from hardware into philosophical instruments. But many physicists, like Ethan Siegel, argue the multiverse is unnecessary and unprovable. They say quantum mechanics math, Hilbert space, explains quantum computing without invoking parallel worlds. Superposition and entanglement, they argue, are properties of our universe alone. Experts like Dr. Bob Sudor urge focus on practical problems, not philosophical speculation. The multiverse remains an untestable hypothesis. Willow does not communicate with other universes. The debate rages on, a dialogue between technological achievement and philosophical meaning. What does Willow really reveal about reality? Quantum computing's impact goes far beyond physics debates. It's a technological revolution poised to transform every aspect of our digital world, from the way we secure information to how we solve problems once thought impossible. In labs around the globe, researchers are racing to unlock the secrets of quantum mechanics, hoping to harness its strange and powerful properties for real-world applications. Its power threatens to shatter modern cybersecurity, which relies on encryption that quantum computers could break with ease. The very codes that protect our bank accounts, private messages, and national secrets could be rendered useless in a matter of moments, leaving sensitive data exposed to those with quantum capabilities. Shor's algorithm could render current encryption obsolete overnight, exposing financial markets and national secrets. The ripple effects would be felt across industries, from banking and healthcare to defense and critical infrastructure, creating unprecedented vulnerabilities. Governments are already preparing, urging a shift to post-quantum cryptography. New standards are being developed, and organizations are racing to future-proof their systems before quantum computers become widely available. This has sparked a global quantum arms race, with the US and China investing billions. Nations are competing not just for technological dominance, but for the security and economic advantages that quantum breakthroughs promise. The nation that leads in quantum will gain immense strategic and economic power. Control over quantum technology could shift the balance of global influence, shaping the future of international relations and commerce. Yet quantum's promise is just as great. It could create unbreakable communication, revolutionize medicine, and discover new materials. Secure quantum networks could protect privacy like never before, while breakthroughs in chemistry and biology could lead to life-saving treatments. Quantum computers could simulate molecules for new drugs, design efficient solar cells, and optimize complex systems. The ability to model nature at the quantum level could unlock innovations in energy, climate science, and beyond. This technology could solve humanity's toughest problems, from fighting disease to managing resources and addressing climate change. The potential for positive impact is enormous if we can harness it wisely. The stakes, both peril and promise, could not be higher. The choices we make now will determine whether quantum power becomes a force for good or a source of new risks. Quantum computing is a double-edged sword. It offers incredible opportunities, but also demands caution, collaboration, and foresight from leaders, scientists, and society as a whole. Its arrival will reshape our world, ushering in a new era of innovation and challenge. The quantum future is coming, and it's up to us to decide how it unfolds. Despite Willow's achievement, we're only at the start of the quantum journey. Building a practical, fault-tolerant quantum computer is a massive challenge. Scaling from 105 qubits to millions is daunting. Qubits are fragile and error-prone. They must be shielded from even the slightest disturbance, requiring extreme cooling. Error rates and fabrication inconsistencies make large-scale systems difficult. Each new qubit adds complexity and potential for error. The next milestone is demonstrating useful quantum advantage, solving real problems beyond classical reach. Researchers are exploring applications in materials science, chemistry, and optimization. The road from Willow's benchmark to everyday utility will take years, if not decades. Quantum computing and the multiverse theory push us into philosophical territory. If many worlds is correct, our universe is just one of countless realities, a shift as profound as the Copernican revolution. This leads to ideas like the simulation hypothesis. Are we living in a sophisticated computer simulation? Quantum mechanics' computational power makes this seem less like fiction. These concepts challenge our notions of free will and consciousness. The quantum realm forces us to confront the limits of our intuition. Machines like Willow expand the horizons of human knowledge and question the fabric of reality. On July 22, 2025, we stand at a crossroads in history. Google's Willow chip marks the dawn of a new computational era. Quantum computers could revolutionize medicine, materials, and AI, but the path is complex. The global race for quantum supremacy brings risks, especially for cybersecurity. The debate over the multiverse highlights the gap between what we can do and what we can prove. The quantum revolution will soon touch every aspect of society. Understanding its basics is vital for everyone. The quantum future is here, bringing new possibilities and questions that will define our century.